Right, Gerhard's going to talk to us today about G-complete reducibility and semi-simplification.
Thank you very much.
Gerhard.
Well, thank you. G-complete reducibility and semi-simplification. G-complete reducibility, Michael introduced that on Wednesday, and he talked about the connection between GIT and G-complete reducibility. Closure of certain orbits being equivalent to a group being G-completely reducible. So I want to emphasize that bridge again and do this in a rational fashion. In the algebraic setting or an algebraic enclosed field, the key was the Hilbert-Mumford theorem, and that said if you have a reductive group acting on an affine variety, you have a closed orbit that's equivalent to saying you can't get outside this closed orbit by means of a cofactor. Okay, the cofactor action exists, then you haven't left that orbit precisely when this orbit is closed. Now I want to do something similar for an arbitrary thing. I want to mimic that. In a general setting. And then the application of all this will be this concept of semi-simplification. So I can say semi-simplification, what is that? Well, we all know that from our representation theory course. You have an algebra that doesn't have to have a semi-simple representation theory. There's some module. Right? You have a composition series of this module, simple quotients. And a semi-simplification of this module would be nothing else but the direct sum of these simple modules. Okay, if you want to do something like that internally for subgroups called algebraic groups. And now, as a last thing before I really start, here's an advertisement for a very new book on the shelves of the best booksellers in town now. You read up more about this because it's all from flying through the.
You put one more copy if you don't pick on it. Sorry. You put one more copy if you don't pick on it.
Yeah, it's well, there's certain things to tell you about the book which are not. But it's available. Which, if you want to read up about this, there's essay of read night, and it's available on the high street. So come and get it. And I should say we don't get any royalties. But no, I'm not. But anyway, it's good. It's a good read for a long time too. So anyway, let me get underway. It'll be quite slow at the beginning and then probably speed up. So the ideas of this semi-simplification, they have a unifying idea of these ideas that are out, as I just said, a semi-simplification of modules for algebras, and we want to do this for a subgroup of a reductive linear algebra group. Potentially, this reductive group is not connected, but it's not really. But the field is arbitrary for now. So, as I said, it unifies concepts that have been in the literature in one dollar. So, semi-simplification would be, you have a module that you pass to subgroup which acts simply on the ambient Kate module K to the end. We'll do this explicitly. So, and then this Mike has already mentioned this whole notion of G-complete reducibility goes back to Sayre. And he already had an idea of he called it a G analog of semi-simplification from representation, where he did this for a subgroup of the K points and G connected. We'll do something which is slightly more general. And the special case of that is actually this concept of Sayre. Okay. And I already said it pops up naturally the representation of non-semi-simple. So let's do this for GLN. The mother or father of all examples is always GLN. We comprehend the example, we know what's going on. Okay. So I have a subgroup, angular subgroup. I can look at a filtration of this module. So it stabilizes a flag, and with respect to super basis, I can get this into an upper block triangular form That's the embedding of this grouping into GLN. And the quotients being these block diagonals, and so these are the sort of symmetrical bits. Okay. And now I'm going to define another subgroup by simply deleting the upper block entries, so setting them to 0. Oh, let's call this subgroup H prime. This consists of the remaining diagonal block elements, the products of smaller GLNIs. And so this new group H prime acts completely reducibly as a direct product of these smaller GLNs or GLNIs on K to the n. So you could call this a semi-simplification of that initial group we looked at. And it sort of almost seems a bit arbitrary. How come we can, what if we're doing different bases than something else is the H prime? So it's pretty clearly this is not unique. It depends on the choice of bases. Okay? But it's unique of the GLN conjugates that's not very good. Okay? So this is sort of a Jordan-Herder phenomenon. And so what we want to do is do this not just for GLN, or an arbitrary connected and non-connected. And we would call this H prime a semi-simplification of H, right? H probably didn't act simply on the K to the n, but H prime does, okay? But if we have to have a formal process, how do I get from H to H prime? I mean, in an E8, I can't just say, well, put a bunch of zeros somewhere in a matrix. I have to find a formula that's taking limits. So that's this idea that I want to introduce next. Degeneration. We'll get a formal way to get from H to this H prime up to conjugacy. So, well, here's what we do. Imagine the sizes of the blocks down the diagonal of N1 to Nr. And then I define a co-character, so a homomorphism on the multiplicative group of my field into this GLN by diagonal matrices A to the R. So little a goes to A to the R, dot, 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 all the way down to the 1, the very end. And I have to tell you how often they show up in occurrences of these powers. And if you think about this, what we'll do is we take the conjugate of my initial subgroup H by the image of this one-dimensional torus. And what it does is it decorates the elements in these upper block entries with factors of A. They get factors of A. And then I can really physically let A go to 0. That makes these entries 0. And so I really do get exactly this subgroup H. So that's the formal way of doing this. I'm really taking a limit and that exists that A goes to 0. Okay? And so what really happened here was I had a subgroup H of the stabilizer of this flag, filter filtration of its module. H lived in a parabolic subgroup, and I ended up with a subgroup in the Levy factor, some Levy factor with a block diagonals. And so the idea is now to do this in an abstract generality. Have this example in the back of your mind as we move on. So I'm going to generalize this to arbitrary reductive G. We don't have matrices. I'm going to do this for E8. So here's the setting. We have reductive K groups, parabolic K groups, etc. Just the notation. So G, once again, is a reductive algebraic group for some fields. K bar is the algebraic closure of K. I'm going to have a notation for the K-defined co-characters, so all K-defined maps on homomorphisms when they look at this group of fields to my group G. And if I wanted to consider that over K bar, I just leave out index and Y instead of all co-characters. Then I can look at all the elements in my group such that if I conjugate by the image of the one-dimensional torus coming from a co-character, right? This is this thing, right? Take an element and conjugate by this an element from this one-dimensional torus, and I look at this limit. If this limit exists, then I stick this element G, little g, in something, a set called P lambda. And it turns out that's a parabolic subgroup in the sense that G modulo this P lambda is a complete variety. We call it in all of our, what do we call it, the Richardson parabolic or R parabolic. Richardson has introduced these parabolic subgroups coming from co-characterism. You find them also in Springer's book. So this is a parabolic that will be the limit, whatever the limit of conjugation by a one-dimensional torus coming from the co-character lambda. And then there's the natural Levy decomposition. You can build that, and you'll see that on this set of co-characters. So L lambda, Richardson Levy or R Levy subgroup, is simply the centralizer of this one-dimensional torus. So nothing happens when you conjugate. So you conjugate, well, wherever that here is. You conjugate, and it's fixed. Okay, so this really is the centralizer of this one dimension. And then the kernel of that viewpoint radical is simply the set of elements for which the limit exists is always constant. And then you do have a semi-direct product decomposition of this parabolic into a Levy and and from now on, H is the sum of its closed subgroup that we want to study and see what we can say about it in terms of this notion of G reducibility, which I'll remind you of. So if I have such a co-character, I can look at the canonical quotient into the Levy, and that's nothing else but take the limit. Okay, look at the limit. Okay? So they're called this map C lambda or CL. I don't have a lambda floating around. I abbreviate that. It's just, mapping this into quotient, and then the kernel is simply this normal subgroup, the uniform. But this is how you see this on the level of this. Now, Richardson's idea, I think Michael mentioned this already, Richardson's idea of studying subgroups was not studying it directly, but say we study G orbits of generating couples of these subgroups. So what we do is we look at the affine variety G to the M, the M-fold Cartesian product of G with itself, and look at the diagonal conjugation actions G on this affine. Well, here it is explicit, right? Very, very straightforward. Okay, later on, this tuple G1 of 2Gn will be a generator for my subgroup and say something different. So I can look at the M-fold Cartesian product of this parabolic subgroup, and by taking the limit of this conjugation action in each coordinate, I get a map to the M-fold Cartesian product of this Levy factor lambda of this parabolic. I also call this map C lambda. It was called C lambda upstairs when M is equal to 1, but I'm also calling it C. And this boldface G is just one of these. Okay. What is G complete reducibility again? Michael has mentioned both of these. Let's do that. So that's the central theme of this talk and indeed of the book. G complete reducibility of okay goes back to Serre. Originally, this is a building theoretic notion, which I'm not going to mention at all. So here's what it says. So I have a subgroup, and it's G completely reducible over K. It's quite a mouthful. I have to shut the K alone. Show GCR over K if provided whenever H lies in a K subgroup, parabolic K subgroup P of G, it actually lies in a K Levy subgroup L of P. Right? This is exactly this analog that we had. This H prime in this GLN was left in such a level. And when I want to do this over the algebraic closure, I just drop the reference to the field. So you say H is GCR. With GCR over K bar. And I'll mention it again later on. Mike has already pointed out GCR over K and GCR over K do not imply one another, independent from. I think Mike showed you a group which was not GCR over K, but GCR over K, but not GCR over K bar. And there's also a down solidity. These things to be treated separately. Okay, so once again, what is GCR over GLN or GLV mean. It's precisely, that means that this module V for H is semi-simple. That's where this comes from. And this is why this is a good term. And it really says what it does on the tin. And it's even better if you stay away from characteristic 2. The same thing is true for classical groups. Okay? In SO or SP, then this module V is semi-simple as an H module, if and only if H is G completely reducible. In that sense, if it lives in a parabolic, it actually lives in a Leviolid. Okay, so that's a faithful generalization notion of semi-simplicity from representation. But of course, this also makes sense for non-classical groups. That was the idea. I can talk about when a subgroup A is G completely reducible. This is purely termed now in terms of subgroups, subgroup structure of that group G. So we've already observed when Mike talked about this on Wednesday, what kind of GCR, what kind of groups are these GCR subgroups? You never leave this class of reductive in the nice class. Sarah's already observed if you have a subgroup which is GCR, then it's actually. But not the other way around. Characteristic 0, the converse is true, but the representation theory characteristic 0 is boring. But in characteristic P, this is far from true. And I've already said it. In general, it can happen that H is GCR over K, but not GCR over K bar, and vice versa. You can't necessarily do one from the other. Sometimes you can, but okay. So now I wanna work towards a rational version of this Hilbert-Mumford theorem that I mentioned at the beginning, and I need a notion. I'm sort of doing this artificially. I'm constructing an artificial idea. Remember, Hilbert-Mumford said that an orbit is closed, it's a risky closed, if you can't leave it by means of a co-character. So then I want to use the idea of a co-character closedness over an arbitrary field. Sort of put in the definition what works for Hilbert. That's the idea. And it sounds like a stupid or dirty trick, but it works. So it is a definition which goes back some years. I have an affine G variety, and I take a point, doesn't have to be a K point. And I say, so this is again a bit of a mouthful, I look at a rational orbit, so G of K acting, right? Not the whole group, it's just the K points acting on this variety. This G of K orbit is called co-character closed over K, to schlepp the K upon. If whenever I take a K-defined co-character and the limit exists, acting with this one-dimensional torus, I haven't left this rational orbit, right? This exists, this limit, but this limit still belongs to this rational orbit. So it's co-character closed. I can't leave it by means of a K-defined. And once again, if K is K bar, this is the Hilbert-Mumford theorem says this is co-character closed over K bar if the limit is closed. That's why we use this term, right? And I'd say that an orbit is accessible from X. A rational orbit is accessible from X over K if there exists a K-defined co-character such that the limit exists and that limit point belongs to this rational orbit. So I can actually get to it. So what good is that? It sounds like a lot of extra words and just to mimic Hilbert-Mumford, and you'll see it. So what's the example? Remember, we want to study tuples. And look at the M-fold Cartesian product of G with itself. Look at a rational co-character, and look at a point in this M-fold Cartesian product of this parabolic, where the limit exists. Then I can look at the limit of this tuple, and then the GK orbit, this rational orbit, is really accessible from this point G over K. So this is the example we have in mind. And so here's this, as announced before, this rational version of the Hilbert-Mumford theorem. I think we do call it the rational Hilbert-Mumford theorem. It does exactly what Hilbert-Mumford theorem does. So we have this G, X, and little x as above, then there exists a unique rational orbit, GK, we can call it, which is co-character closed over K, and it's actually accessible from X. So this is an arbitrary field now. It's not just the algebraic close. So what is the connection with GIT? What is the connection with? Well, here it is. So there's a technicality which I'm going to throw at you, but it's not all that difficult. So I look at some embedding of my reductive group, and I look at it. Let N be the associative matrix of all n by n matrices over K, and then I say if I have a subgroup, I take a tuple, an n tuple of points in that subgroup. And I call that tuple a generic tuple for H. If that tuple, the elements of that tuple generate the same subalgebra of this associative algebra Nn as is generated by the whole group N. You always make M big enough to find such a tuple. For instance, you could take a topological generating. Michael told us what a topological generating is. The tuple such that if you take the subgroup generated by this tuple, take its Zariski closure, that's the whole group H. If you don't like this generic topological generating. Okay. It's helpful that this doesn't have to be a K point. So if H is a generic tuple, then you can conjugate, and that's a generic tuple. Conjugate, that's not difficult. So here's the theorem, which I've alluded to at the beginning. This is the connection between the representation theory and the GIT geometry. This was first proved in the algebraic setting by my two co-authors, Michael Baden and Martin, who are happily in the audience to answer any questions. Sebastian Helfer from. So what does it say? And it's really, that's the crucial tool to get off ground. So I have a subgroup, I pick a generic tuple, as I said, this always exists. And then H is G completely reducible. So that's a purely algebraic notion. Like if it's a parabolic subgroup, it's in a Levy subgroup, that parabolic subgroup. That's the case if and only if this rational orbit, G of K of this tuple, is co-character closed. And that's a geometric statement. Okay? And so in the algebraic setting, it's completely reducible over R if and only this orbit is Zariski closed. So this is the connection between the geometry and the representation. This is an extremely powerful tool. And it turns out to be an extremely powerful tool. Okay, so that's this first. So what about semisimplification now? What does this have to do with that? But do something along the line here we've done with the DLN example at the very beginning. So here's the definition. I have a subgroup again, H. I have another subgroup H prime. Remember, we had an H and H prime in GRN. Same situation. We call this a K semisimplification of H. We need to have the K along. If there exists an R parabolic subgroup, like a Richardson from the P lambda before, K subgroup P of G in an R Levy subgroup L of P, such that H sits inside of P, and the H prime is the projection of H into the Levy factor. And H prime is actually G completely reducible. So this pair, P and L together, they yield semisimplification. We've seen that in the explicitly in terms of matrices in this example ahead. Okay, so this is a K semisimplification. So that's the second term of my title. Okay. Now you can ask, well, does it even exist? It's like possibly a little bit too much to ask for. It existed in this GLN example, but in general, I mean, we'll get to it. The easiest example, what if this subgroup I start with is already GCR? Then I don't have to go anywhere. Then it's its own semi-simplification, and the parabolic subgroup together with its levy is G with itself. Okay. Well, you know, it's a naive example, but fine. Okay, so G completely reducible subgroups fit into the scheme. What about if I have a pair which yields a K semi-simplification, and look at another Levy subgroup? Another Levy subgroup of P is the conjugate by an element from the unimportant radical. And it's easy to see that that other Levy subgroup together with P also yields a simplification. That's just a conjugate of my subgroup CLH inside of P. Okay, you know, so really it's the parabolic that yields a semi-simplification. And as I indicated at the beginning, connected G and subgroups of K points of G is generalized Sayre's genealogical simplification. Sayre, in this notion, picked a minimal parabolic subgroup containing H, and then if you push this into L, it has to be irreducible. That's a special. Okay, that's a K semi-simplification. Fine. So what we aim for is like a Gerhard Röhrle theorem, that this K semi-simplification. We know already in this GLN example, it's not unique, but it's unique to conjugacy. See that. But first of all, let's look at existence. I mean, it could be that we're chasing a red herring, you know, only exists. Because we've seen it in GLN, doesn't mean it exists in other places. Well, here's what you do. You take a generic tuple, and imagine H lives inside of your R parallel except P lambda, and the C lambda of H is the generic tuple for the image of H in this Levy. That's easy to see. So by this theorem above, you know, this equivalence of co-pair closed orbits and GCR-ness, the C lambda H is a K semi-simplification if and only if this rational orbit of this point C lambda H is co-pair closed orbit A. When you use exactly this geometric characterization, okay, but how on earth can I manufacture such a co-character closed orbit? Well, yes, I can. I just use the existence statement from this rational hypertonic. Okay? There always exists at least one such case. Here it is. You just pick a suitable lambda, a K-defined co-character, such that this rational orbit of this thing is co-character. So the C lambda is indeed a K simplification of H, and it's given by this pair P lambda that just drops out for free with this machinery. Okay. And as I said, we want to have a sort of uniqueness up to conjugacy, like the Gerhard Röhrle thing, right? Gerhard Röhrle would say, well, if you have a composition series, that's not unique, but the simple bits you see are the same of the order. That's basically. So what you need, I need this later on, that when I have a K semi-simplification, there always exists a K-defined K co-character, which such that this semi-simplification is really yielded by the lambda. So here's this main result, and it's been proved in the special case for the algebra you posted quite some time ago in joint work with Ruhr-Universität. So imagine I have a subgroup again. We've already agreed that K semi-simplifications exist, but they could have nothing to do with one another. But this turns out, well, if you have two of them, then they're conjugate under the group of rational points. The best you can. Well, we've seen already in the GLN example that we're not unique. If you choose a different basis, you get a different set of. Well, the proof is not really completely trivial. It uses a little bit of algebraic group theory, sort of descending chain argument. I'm not going to show it. And so this is what we would call a Jordan-Wilker theorem for subgroups of
When you say descending plane, do you mean like the theoretical inductive functions or?
yeah. Okay. Let's do examples again. Well, very silly ones. The silly example is again, if I have a GCR subgroup, it's a case in this figure itself, and the other by the pair, of course, we've seen that. What if I take a non-reductive subgroup? But if H is a parabolic subgroup, you can say a parabolic case, that's obviously not GCR. It's not reductive. You take some Levy subgroup, then this pair P L yields a case simplification, namely L of P, okay, for free. Well, and if I have a different, or if I have a conjugate, a GK conjugate of L, then that can only be a case simplification of P if it's also inside of it. So nothing new. So you can play around with this notion. Okay, I think once again, a case semi-simplification and a K-bar simplification in principle have nothing to do with one another because GCR over K versus GCR over K bar are independent of them. That's just another message from that. But in fact, these notions seem so similar, and generally you can't deduce one from another and vice versa. Okay. In the second or final half, I'm gonna want to do the same thing for the algebra. This hasn't surfaced yet, but there's a notion of complete reducibility for sub-algebra, the Lie algebra of G. And the action is not conjugation, it's just the adjoint action. Everything works the same way. And in fact, many things are easier because it's a linearization of the algebraic groups. So let's go through that. We've seen everything that we've seen before in the group setting. We'll see again in the Lie algebra setting. And it's not particularly, not any more difficult. And at the very end, I say, what does semi-simplification in the subgroup setting have to do with semi-simplification in the Lie algebra setting? And I think you come back to those. Okay, let's get out of the way. So factor G is the Lie algebra of my reductive group G, and as I said, we act on with the adjoint action. This is common. Then conjugation action itself and the adjoint action are related by the derivative of the conjugation action is the adjoint action. Will play a role later on. And to simplify notation, I just write G dot X. In the context, whether X is in the group, then it's conjugation. If X is in the Lie algebra, is the adjoint action. Just don't want to write it out differently. Then again, we do the same thing. We act on the Cartesian product, or I can take X to be either the Cartesian product of the group itself m times or of the Lie algebra, the direct sum, and let G act diagonally either by the conjugation action or by the adjoint action. Okay. It's fine in both cases, I find best variety. And then what are the Lie algebra of a P lambda is factor P lambda, the Lie algebra of L lambda is factor L lambda, etc. There's a description of them, okay, in terms of existence of limits. So if X is in this factor P lambda, if and only this limit exists, and this time it's the adjoint action, we have to differentiate that. And if it's in the Lie algebra of the L, the capital L lambda, that is true if and only it's fixed, and it's zero, limit exists in the zero if it's in the Lie algebra of the unipotent value. Not any more complicated than we see it before. And again, projecting onto that direct sum end, L lambda, is just simply taking the limit, okay, in this language. Okay? This is the usual projection of my P lambda onto L lambda in the Lie algebra. Kernel is the I don't think I gave it a name. This is a Lie algebra. That's completely analogous to the group setting. And once again, I want to use the same notation for the n-fold Cartesian product. So I can map factor P lambda to the M into factor L lambda to the M just by simultaneously taking the limit at each coordinate. This is not any different than before. So I call this map again C lambda, just as I did in the concept. Okay, so this is the setup, and then we'll see again now that all these terms that we've seen before, complete reducibility and symmetry. So what is it? G-complete reducibility of subalgebras. Well, I mean, you could do this now with your eyes closed. So what is it? In the algebraic closed setting, McLinch has done this quite some time ago, and he did it in the rational setting. He did it with Herbold some years later. So a subalgebra, an arbitrary subalgebra of the Lie algebra of G is called G completely reducible over K. Well, if for any K parabolic subgroup P, it lies in whatever it lies in its Lie algebra, it actually lies in the Lie algebra of a Levy K subgroup L. They're completely analogous. Nothing, no surprise. And if I do this over K bar, I just leave off the reference to the perfect sense. And you'll ask yourself, what's the connection? Here's the connection. Suppose I have a subgroup, K defined, and suppose the identity component, that's this H over naught, is G completely reducible over K in the sense that I defined. If it's in a K defined parabolic subgroup, it's in a K defined. Well, then the Lie algebra itself is G completely reducible over K in the sense, the definition of. So in the algebraic closed setting, this was done again by McLinch, and we've done it together with Laura Focus-Berger quite some years later. Okay. And interestingly, this proof in the algebraic closed setting is used as an optimality argument. I think Mike mentioned optimal parabolics, optimal co-characters in the algebraic closed setting. But for an arbitrary field, that doesn't exist. And so if we only prove we know this, but the GCR subgroup predicts the GCR, the subalgebra, the algebra. The only noticeability theory are using the fit-centered thing. I'm not going to say anything about it all. Well, to set it over K bar, you can use an optimal stabilizing co-character, but that doesn't exist for arbitrary K. It's not working. So sometimes, and I think Mike indicated that sometimes there's building theoretic arguments that are very elegant, very smooth, and you can use them, and there's no counterpart on the group theory of contour. Okay. Now, it's a natural question. What about the converse? What if the Lie algebra of H is G completely reducible? Does the initial subgroup G completely reducible? But the group says that it's false. Ben Martin has already given a counterexample in the algebraic closed case. It prevented synomorphisms involved. So, again, we want to this rational Hilbert-Marquardt theorem is the right setting to have a geometric criteria for G complete reducibility of algebras for algebras. So this is almost the same thing that where you saw group elements before, they're now elements of the Lie subalgebra. So H is a Lie subalgebra of G really. That could take a tuple, and I call it a generating tuple. Well, if it's a generating tuple, I don't even need generic. So if these elements generate H as a Lie subalgebra of vector G. Yeah. So, well, let's see. Here's the connection again. This is this counterpart to the geometric characterization of G reducible over K. Now for Lie subalgebra, so I have a subalgebra of the Lie algebra, this reductive group. I take a generating tuple for this subalgebra. I let G act on G to the M by simultaneous conjugation. Well, react on action. then this subalgebra is G completely reducible in this algebraic sense. Right? Living in the Lie algebra, K-defined parabolic, and it's in the Lie algebra of a K-defined algebra. If and only if the rational orbit, the GK orbit of this point is co-curved and close to the K. I can use exactly the same technique for that. And this again leads to the notion of a K simplification. We do the same thing. Let's see, but that didn't exist before. I have a Lie subalgebra of my Lie algebra factor G, and I say that another Lie subalgebra is a K semi-simplification. I have to drag this K along, of H or G really. If this is a K-defined parabolic subgroup of G, the Levy K subgroup, such that whenever H is in the Lie algebra P, it actually lives in the Lie algebra. And this H prime is G completely reducible. Okay. And again, I say this pair yields H prime. Same questions, existence and uniqueness up to conjugacy, we prove the same thing. Okay. Triple example again, if the subalgebra is already GCR over K, well, it's its own semi-simplification. You don't have to do anything else. It's simplified. And the same analogous statement. What if I have a different Levy subgroup? Well, then they conjugate a rational point from the uniform radical. So it's really the parabolic that yields a semi-simplification rather than the pair. Okay. Existence is the same. It's really the same thing. Goes back to the rational, the Mumford theorem. Let's go to that quickly. It's even easier. So I have a subalgebra. I have a generating tuple, and then taking the limit along a cocurve gives a generating tuple for the algebra that we get by mapping it along this the C lambda into tractor lambda into some Lie algebra L sub lambda. So this is a K simplification of H, if and only if this rational orbit is co-curved to closed over K, by this theorem that I just showed you. But it follows from the rational Hilbert-Mumford theorem. Again, it's the same application we've seen another second time, that there's at least one K simplification. Take K, take a lambda such that this rational orbit of this C lambda H is indeed co-curved to closed. This exists by the existence statement of this rational Hilbert-Mumford. So this is indeed a K simplification yielded by the pair P. Now almost child's play to do this again. And then you prove, yes, two such K simplifications, they're in fact conjugate from the adjoint action of G. Okay, the proof is much easier than in the group case. And it's just, you just use the uniqueness statement of the rational. Okay. Last and not least, what does a K simplification of a group have to do with a K simplification of the Lie algebra? Well, they really come together, they're compatible in that following sense. I think this is the last thing I'd like to show you. And again, it goes back to work of Martin and Bate and Böhm and Toggesberger. I have a subgroup and I have its semi-simplification, H prime, and then what does the H prime have to do with the semi-simplification of H? Well, it's a semi-simplification of the algebra. It's sort of, it's as good as it can be. Okay? And maybe I can give you a proof here. So by this earlier lemma, if I have every semi-simplification is yielded by a pair P lambda L lambda, and then the H prime is really the C lambda of H. And so it follows from this other theorem I showed you that the Lie algebra of H is GCR over K because H prime is GCR over K. And then the differential of conjugation is the adjoint action. So I have D of C L lambda is simply this pushing into the Lie algebra of L lambda. So therefore the Lie algebra of H prime is just the image under this pushing the Lie algebra of H into of Lie H. And so the same pair also yields semi-simplification. It really is this Lie algebra stuff then fell off the log once when we should have officially the group setting. Right. Thank you very much.
We have questions.
Yeah.
Right next to it, where do you define the kind of the cocharacter action on the Lie algebra?
Yeah.
I think really so. Was that defined for a K cocharacter, or was it just another to it?
Okay, yeah, for K-defined cocharacter. If I want to talk about G complete reducibility over K, I need to have a K-defined cocharacter. Yes. So
My problem is I've already asked you all of my questions.
Oh, okay.
Yeah, that's fine. You got all my questions already. Any further questions for Gerhard?
yes, sure.
It's a PDF of the book available online.
No. We're not allowed to.
I'll have to ask my life.
Yeah, we have to that's live on the box.
So that's again, it's available in the high street. And so you asked. Okay. Available to purchase.
That's what, yeah. So if it was available on, on the Woodfield the archive, we weren't allowed to publicize it. We've signed our life over it. I think he's in trouble. Either you well, no.
Very working around the building here.
Is there any way around?
There you have results in the building.
There's one example that I had there. There's one case. What did Mike say? Mike said yes.
He said yes.
Yeah, I think we believe we know. But whenever Mike says yes, I believe him. Not at the time. Not at the time. But it well, there's people who would say the building theoretic approach is the correct one. That's at present that's more powerful. I mean, up until another thing is written down, there is no as we stand, there is no optimality for an arbitrary optimality notion for an arbitrary field. Optimal K-defined cocharacter, we don't know what that is. Perfect fields is much better. Algebraically closed fields, we can do this, but not yet.
All right. If there are no more questions, let's thank Gerhard again.